Now that we've done the basics of solving simple trig equations using the unit circle or the calculator and reference triangles, we can solve more complex equations. And there's 5 types of equations we're going to look at. Single trig functions, which has only a single sine, cosine, tangent, secant, cosecant, cotangent in it. Multiple trig functions, where I've got different sines, cosines, tangents combined in the same problem. Functions that involve multiple angles being 2 thetas, 3 thetas, 4 thetas. Quadratic form with a single trig function, and then quadratic form with multiple trig functions. Quadratic form just saying I'm going to have squares in there like a quadratic function. So the preliminary goal whenever I'm solving these trig functions is I want to isolate the trigonometric function involved in the equation. Just like with equations back in Algebra 1, if I had x plus 4 equals 6, I subtracted 4 from both sides to isolate the variable, or isolate the x. Here I want to isolate the trig function on one side of the equation. So here are the 4 steps that we're going to follow. First of all, we're going to perform your algebraic operations until you have a quantity that is only a trig expression. And in other words, move everything to the other side so that you only have a cosine of x, or a tangent of x, or a sine of x. Step 2, take the inverse trig expression to get the expression with the variable by itself. And in other words, you're going to take sine inverse, cosine inverse, tangent inverse, or arcsine, arccosine, arctangent to both sides, just like we did up here with our sine inverses to both sides. Finally, get the variable by itself. We'll need to do that if there's more stuff inside the sine, cosine, or tangent function. And then finally, write the answer in terms of what the question is asking. Sometimes you're going to want all solutions, and you are going to have an n in there if you're going to have all solutions. All solutions means all coterminal angles that go on forever. The second part is if you have a specific domain, limit your answers to that domain. So if I only want from 0 to pi, you don't need to find the second half of the unit circle. So look at what the question is asking you. So the first couple of examples here is we're going to solve the following trig equations for all solutions in pi radians. So you might want to have page 86 off to the side just so you can see these steps to start off with. But I want to get my trig function by itself. So I want to get the cosine of x by itself. I'm going to move all the other pieces to the other side. So doing my rules of algebra, I'm first going to subtract the 1 to both sides. Then I'm going to divide by -2. So now I've got the cosine of x is equal to 1/2. This is the step, now that I've got my trig expression all by itself on the left-hand side, I'm going to take the inverse trig to both sides, in this case the inverse cosine. And this is just what we did in the previous examples. So here, the cosine inverse of the cosine of x is equal to the cosine inverse of 1/2. Now my cosine inverse and cosine cancel out, so I'm left with x is equal to the cosine inverse of 1/2. And 1/2 is on the unit circle, so I don't need to use the calculator for this one. I can pull out my unit circle. And the cosine are the x values, so my x values that have a value of 1/2 are right here, the pi over 3, and right down here, the 5 pi over 3. So the two x values that I'm going to have are pi over 3 and 5 pi over 3. And I'm not quite done yet, because I don't say find the answers from 0 to 2 pi. I say find all solutions. So I need to write this expression in an equation that represents all solutions. And the easiest way to do it is just to put a plus 2 pi n at the back. So here, x is going to be pi over 3 plus 2 pi n, and x equals 5 pi over 3 plus 2 pi n. where n is any integer. And all this back piece is saying is every single time around the unit circle. So if I plug in a 0, I haven't gone around the unit circle once yet. It's just my original answers. If I plug in a 1 here, it's 2 pi plus pi over 3, which is going to give me my next time around the unit circle. If I plug in a 2 there, it's pi over 3 plus 4 pi then. So that plus 2 pi n just tells every single time around the unit circle. And if I were to go in the negative direction, I'm just going to go in the clockwise direction. So I could put in a -1 there, -2, -3, and just work in the opposite direction. Problem number 2, tangent squared of x minus 3 equals 0. So for this one, I'm going to add 3 to both sides. So tangent squared of x is equal to 3. And then I'm going to take the square root to both sides. So the tangent of x is going to be plus or minus the square root of 3. When you take a square root, make sure you keep the plus or minus. So really what I've got is the tangent of x is equal to the square root of 3, and the tangent of x is negative square root of 3. Next piece that I need to do is I need to get this x by itself. So tangent inverse of the tangent of x is tangent inverse of square root of 3. And then same thing for the other one. The tangent inverse of the tangent of x is equal to the tangent inverse of negative square root of 3. So my tangents and tangent inverses cancel out on both equations. So I've got x is equal to tangent inverse of square root of 3 and negative square root of 3. So once again, I can go to the unit circle for this one because square root of 3 is on the unit circle for tangent. And I want to find plus or minus square root of 3. So I've got a positive square root of 3 here at pi over 3. I've got a negative square root of 3 here at 2 pi over 3. Down here I've got a positive square root of 3 at 4 pi over 3. And then I've got a negative square root of 3 over here at 5 pi over 3. So I want to include all 4 of those answers. X equals pi over 3. X equals 4 pi over 3 were my 2 answers that were the positive versions. And then I have x equals 2 pi over 3 and x equals 5 pi over 3 for my negative square root of 3 answers. And once again, because I want all values, I need to put this plus 2 pi n, where n is any integer. So I've got 4 solutions for that one. The last example, 13 sine of x minus 1 equals 0. We'll start by adding the 1 to both sides. Divide by 13. So I've got the sine of x is equal to 1/13. Take the sine inverse to both sides. So sine inverse and sine. So x is equal to the sine inverse of 1/13. Now this is one that I cannot do using the unit circle. 1/13 is not on the unit circle, so I have to go to my calculator for this. And for this, I've got to make sure my mode is in radian mode. So we'll start sine inverse of 1 divided by 13. And I get this radian measurement, 0.076999147. So I know my first solution is going to be 0.077, rounded to 3 decimal places. But I know I need a second answer. So I'm going to have to draw a reference triangle for this. Now here's probably the most difficult part, is that since we're in radians, Over here's 0 pi. Here's pi over 2. There's pi. We know pi is approximately 3.14, and pi over 2 is approximately 1.57. So 0.077 is going to be somewhere over here. And I know that's not drawn to scale at all. But my angle is 0.077. Sine is positive here. So my two quadrants that I'm going to draw my reference triangle in are the first and the second, because sine is positive in the second quadrant. Now the angle I need to find has to start at 0 here and go all the way there. So really what I'm looking for is that more bolded angle. And I know the whole length here is 3.14. And if this is 0.077, that means this total distance has to be 3.14 minus 0.077, which is going to be 3.063. 3.14 minus 0.077 is 3.063. So my two answers for this one is going to be 0.077 plus 2 pi n, and x equals 3.063 plus 2 pi n. And that's once again where n is any integer. And we need to put this plus 2 pi n at the back because we want to find all solutions in pi radians. So for this one, my first answer came from the calculator. I have to look at the second quadrant that is not defined in the original function and then find that solution manually using reference triangles.